Good afternoon, everyone. My name is Mona Hella, and I've been at RPI since 2004. What you see here is a picture of the students that I graduated since I joined RPI. These are the students who really were part of my journey. The work that I'm going to show here is basically their contribution. I run my lab, and it's called Rensselaer Integrated Circuits and Systems Lab. This is my email. This is a picture of my current students. I think those of you, who have been with us at RPI have seen some of them as TAs, and this is a picture in the dining hall. Hopefully we'll be there in the fall and we get to see all of you. So what I do, I design electrical and physical, in the electrical and physical design of integrated circuits, basically microchips. So I'm a chip designer. This is the picture that you see here. These are the circuits that we built. If you have taken classes like Introduction to Electronics, Analog IC, Digital IC, you have worked with these transistors. We design them electrically, and we build the layout. We submit them to a fab, and we receive the picture that you see on the right, which is the microchip. These are millimeter by millimeter scale circuits. And my first chip was back in 2005. This was a multi-standard radio. I think all of you on your phones, you have chips that are geared towards different standards and different functions. You have Bluetooth functionality, you have wireless LAN, you have, of course, the cellular standards. So you have some of these on your chips, not necessarily mine, but these are similar designs to guarantee to or to work in different standards depending on where you are. So this was in 250 nanometer technology. From the designs that you have seen from Professor Schur and others, you know that the technology scales down. So this was back 15 years ago, and we were using 250 nanometer. This is the channel length. Now, these are some of our recent work. This is a 150 gigahertz radiator. You can see here there is an antenna on chip. So now we have the antenna there. And this one on the right is actually a collaboration with another university where we are building time-of-flight sensors. This is under LISA, and it is working at a wavelength of 940 nanometer. So right now, what we are using, not 250 nanometer, we are using 22 nanometer devices, and we are using silicon photonics technology, where we are integrating photonics and electronics components. So building system on a chip to serve many applications. So why are we doing these chips? It's mostly for future wireless and sensing applications. So 5G radio going to 6G radio, optical wireless or visible light communication. In terms of sensing, and again, Professor Schur and Professor Karlasek, and we all work together, we are using the terahertz frequency range for sensing applications, for safety, for additive manufacturing. We're doing time-of-flight sensors and biomedical interface ICs. All these system on a chip, they need to be powered. So again, Professor Jan San works at power levels of watts and kilowatts. The power level that I use in my microchips are in the milliwatt or microwatts or below. So we need what's called a power management circuit, and this can either be a battery, or it can just harvesting energy from the environment. This is examples of some of the research that we are currently doing. This is a health monitoring system, so it has something called analog front end or the electronic readout. The electronic readout has the sensor interface, has power management, has communications, and then it has to interface with either your mobile phone or with a reader. These systems have to be really sensitive to detect the difference between a normal biosignal and a signal, for example, when you have a heart attack and there's a different signature that has to be reported. So we built some of these in 180 nanometer technology. This is an example of the analog front end and EDC. And this is a picture of my students in the Mercer lab. The Mercer lab is in the 6th floor. and it has, a number of really good equipment for different applications. And they are testing this to measure ECG, EMG, and EEG. These are the signals from the heart, from the muscles, and from the brain. All right, so this was here developed at RPI, and we have a number of publications on that. Communication system is at the core of what we're doing. Most of the 5G systems that you hear about, these are based on beam steering and line of sight. So you have to build special circuits for that. You really have to understand the digital communication requirements, system linearity. You have all seen signals and systems. You have been in signals and system classes. So the linearity of the system is important. And these are examples of these chips. So now we are working on 6G technology, which is basically using frequency ranges that are 10 times or more than what you have. So the wireless standards now are up to 6 gigahertz. 5G is going to be, and 5G new radio is 28 and 39, and we are now looking into the use of above 100 gigahertz. We are also using this band, as Professor Shur mentioned, for terahertz application. Terahertz is above 300 gigahertz actually, but sometimes we refer to anything above 100 as a terahertz, and we are using it for spectroscopy. This is a collaboration with mechanical engineering and physics, and you see here some of our chips for generating these signals, and we use them actually to detect ethanol and methanol and other gases in the lab in the 7th floor. And finally, this is a work under LISA. This is time-of-flight sensors. This is an example of electronics photonic integration. You have a number, you can also do beam steering in the photonics domain as well as on the millimeter wave frequency range. This is all the passive photonic structures. You also have electronic systems. You have the receiver, you have amplifiers, you have analog to digital converters or time to digital converters. So it's really a very nice combination of understanding the device physics, understanding photonics, understanding the interface between the device physics and the circuits and the systems applications. All right, and this is really done for all these things we heard about human-machine interface, robotics, automotives. At the heart of all these applications is a microchip that does different functions. And hopefully I introduced you to my research. I have my email in the first page, and I think some of you already know me. So with that, I end my slides.